Hello everyone, welcome to the channel. This is Firjana. In today's video I'll be going over hashing. You probably have already learned about linear search and binary search. Hashing is another searching technique which would help us search for value with given key. In this video, we will be discussing the type of hashing to solve collisions. So here we defined two functions for hashing. One function that is one-to-one function, which actually uses more space. And then the second function is that taken modulo with the size, which actually help us save space. So two terms we should be familiar with: the key space, which is list of element, and hash table is the position where each of those elements that are given to us should go. Alrighty, so let's do an example using the one-to-one function and explain why it is actually using more space. We are given the following values. We want to find position where these values should be placed. We have 10, so have h of 10. 10 equals to 10, and then h of 3 equals to 3. So these are basic one-to-one function and so on. If you look at that, for the first value 10, I don't have a position in my table. Well, I can make my table bigger, so I can add more spaces. However, would that actually help me save space or use more spaces? And lengthwise, we have fewer numbers of elements that we are storing in this table. However, let's say we have huge amount of number, and let's say we have 10,000 right after 30. So 10,000 would go probably huge amount of indexes after 10,000 would be placed. Then what would happen to those empty spaces that we have? So let's say we'll have the empty spaces from here, and then it would go until 10,000, and then 10,000 would be placed, right? That is why it's better to apply the second function, which actually calculates using the size of the table, and it places the number, the value we have according to the size. H of 10 would be 10 mod 10. The size of our table is 10, and that would give us 0 index. And then we'll have 3 mod 10, and that would give us 3. If you don't know how to calculate modulo, you can actually look it up. There are some videos on YouTube, or you can use an online calculator which does the calculation for you. 10 goes here, 3 goes right here. Let's calculate for 8, and 8 goes right here. However, you can see when we come down to value 13 mod 10, that is 3. Where would this go? The third position is already taken. Okay, so this is where the collision occurred. We have to find solution for that. We have two categories for solving collisions. One is open hashing, which actually is the chaining method, which is linked list. And then we have closed hashing, which is the probing method. And for that, we take linear probing, and then we have quadratic probing. Okay, so linear probing is to place on the next available space in linear term. And quadratic probing is to place on next available space at quadratic time. Every time you square that counter. Right, let's actually solve this using chaining. We have 10 mod of 10, because our table size is 10, and that would give us 0. We have 10, no, actually this is 3. Our value 13, table size is 10, that would give us 3. All right, and let's see how the chaining works. So what you do, you create linked list. Goes like this. So we'll place 10 here. Okay, we'll do same for 3, and then we'll do 13 here, because since both have same position. And then 13, and then if we're to have more values that goes at the position 3, we will apply more value in the list, so the list could go forever. And then let's not forget about 8. This method does help us with actually solving collision, so we don't have any more collision. However, when we have to search for, so let's say we're searching for 13. So first we have to look at 3. We'll say, oh, 3, it's not 13. Okay, then we'll go to the next element on the list. Oh yeah, 13, we found it. But let's say, what if we have all the element up until, let's say it's a huge number. So we have to look at each term elements before we can actually reach the element that we're searching for. So this method is not helping us in this term, where we have to search the entire list to find an element. Is of x, that would equal to the value given plus counter. In our case, we could call the counter n, because the counter would start at 0 and then it could go until however many number element comes after it. And then we take modulo of that, and that's the size. In our case, our size is 10, so we'll just write down 10. The size could vary per table to table. So our table, we already set size, we got 10, so we would multiply with take modulo of 10. So we have 10. Our first counter is 0, so we'll have 0 mod 10, and that would give us index of 0. And then we have 13 plus 0 mod 10. Okay, now it's 3. This is where we actually apply linear probing. So since it's 3, we will increase our counter. So now our counter would be 13 plus 1 mod 10, and that would give us 4. And so if I were to place these in the table, the values, we know that 10 goes here, 3 goes in the 3rd position, 8 goes in the 8th position, and then 13 goes right here, since it's the next available position right after the original position we were supposed to place that. Since that one was already taken, we applied that into the next available position. Let's say 4 was taken, we would have applied into the next available position, and then next, and then next, and then next, so on. All right, this method also causes cluster. Okay, to avoid clustering pattern, we apply the quadratic probing. Plus 0, 0 square, 0 is just 0, mod of 10, that's 0th position. We have 3, and then we have 13 now, so 13 plus 0 mod of 10, and that's at 3rd position. So we do probing, so we have 13 plus 1 square is 1, that's 10, and that is equal to 4. Alrighty, so for quadratic, we will have 13 go here. It's similar to linear, however, so since we have 1 and then we found an available position, okay, so let's say we add another element, so we have 4 plus 0 modulo of 10 is equal to 4. Alright, so So we'll write 4 here, just to show you how the quadratic proving is working. So when we came down here, so you can see when we took the counter of 0, that third position, and then we took counter of 1 square, that gave us the fourth position. However, that is also filled, so we would apply increase a counter. So we'll have 13 plus 2 square is 4, modulo of 10, that would be 7th position. 13 will go right here. So you can compare how drastically the position of 13 changed. However, if we were to have 4 here, and our 13 would have been still here because it's the next available position in linear order. However, it's in quadratic order since it's in the 5, so it would be the quadratic order, so that would be placed on the 7th. All right, so hopefully that is making sense to you. However, that is also an issue because this causes us secondary cluster. Just to give you 30-second recap of what we have done so far, we have defined hashing is basically a searching method of searching for a value with given key. We defined a function of 1-to-1 which uses more space, and then we used the alternate function that actually help us save space. We used the first function, 1-to-1 function, second function which helped us save space. However, the second function caused us collision, so we applied the chaining method to resolve collision. The chaining method, it has to go through each element on the list, so we actually moved to proving because it's placed at the next available position on the table. It's easier for us to find, and we know that it's just right next to 13. If it's filled, then we go to the next position, we go to the next position, we go to the next position. However, that caused us clustering also, so we actually tried applying the quadratic proving where you take square of each counter, but that also caused us secondary cluster. Next video, I will be actually discussing how double hashing is helpful in terms of resolving collision.